So in this video I would like to talk about partial derivatives. Partial derivatives are really important in the study of partial differential equations such as Laplace's equation or the heat equation. Now, calculating partial derivatives is not actually any harder than calculating regular derivatives. If you know how to calculate the regular derivative of a function, then you automatically know how to find a partial derivative. The best way to show you this is using some examples. So let's suppose I've got u of xy is equal to x squared plus 2y squared. So u is a function of two variables, x and y. U depends on x and y. When we take the partial derivative with respect to one variable, so for instance du by dx, we treat the other variable as a constant, in this case y. So if I were to find the partial of u with respect to x, I would treat y as a constant. So let me show you what I mean by this. So let's find the partial of u with respect to x first. So the partial of u with respect to x. That's sometimes denoted as u subscript x, or equivalently, that's the same as the partial of u, that's the curly d, with respect to x. So how do I calculate this? Well, I just differentiate anything with x in it as usual. So the derivative of x squared is just 2x. Now, I said that I would be treating y as a constant. So if y is a constant, then y squared is also a constant, and 2y squared is also a constant. So the derivative of this whole thing is just 0, because the derivative of a constant is 0. So the partial of u with respect to x is just 2x. Now let's find the partial of u with respect to y. That's the same as the partial of u with respect to y in this different notation, but it means the same thing. In this case, I treat x as a constant, but y as a variable. So if x is a constant, then x squared is also a constant, so that's just 0, plus the derivative of u with respect to y. So I'm now going to find the derivative of this thing with respect to y. The derivative of 2y squared with respect to y is just 4y. So the partial of u with respect to y is just 4y. I just treated the other variable as a constant. This is not just limited to one derivative. I can actually take the derivative again, so I can find a double partial derivative if you like. So for instance, what is the, or how can I calculate u sub x? That's the second partial derivative of u with respect to x. So how do I find the partial, or the second partial of u with respect to x? And this is the notation used. It's actually the same notation that we might use with regular derivatives, except I just replace the d's with curly d's. Except in the case of mixed partials, but that's another video. So, well, I know that the derivative of u with respect to x is 2x, so if I again take the partial with respect to x, I just get 2, because the partial of this thing with respect to x is just 2. Likewise, I can also do the same thing here. I can take the second partial of u with respect to y, again, that's the same as the curly, or the partial derivative of u with respect to y twice, which is just 4. Right, because the derivative of 4y is just 4. Let's look at another example. Let's look at f of x, y, and t. So now f is a function depending on three variables, x, y, and t, and f is equal to x squared y plus sine t. Let's first try to find the partial derivative of f with respect to x. Well, what is f sub x? Or if you like, the partial of f, let's make that more legible, so the partial of f with respect to x. Well, I know that sine t is just going to disappear, so now all that remains, all that remains is I've got to deal with this thing, x squared y. Well, in this case, x squared y, well, I'm treating y as a constant, okay? So if I had 2x squared, how would I differentiate that? If I had 10x squared, how would I differentiate that? I always had a constant, or a constant coefficient. In this case, I've got y times x squared, and y I'm treating as a constant. So you could think of this as, I guess, yx squared. And this thing here is a constant, this y. We're treating it as a constant. And so, as a result, if we differentiate this with respect to x, all we get is 2yx, or 2xy. We treated y as a constant. Plus 0, because we've got a t here. So that's the partial of f with respect to x. we can do the same thing by finding the partial of f with respect to y. So what's that? Well, again, I can do the same thing. So what's the partial of x squared y with respect to y? Well, if you think of it this way, x is also a constant. I'm treating x as a constant here, so x squared is again a constant. So I've got a constant times y. And if I've ever got a constant times y, like 2y or 3y, the derivative of that thing is just the constant again. So the derivative of this thing with respect to y with partials is x squared. Sine t depends only on t, so this thing just becomes 0. So the partial of f with respect to y is just x squared, and obviously an alternative notation for this is the partial of f with respect to y. Let's do the same thing for t. For the partial derivative of f with respect to t, or equivalently df by dt, that's just 0 because this expression here does not depend on t, but this does. And what's the derivative of this thing with respect to t? Well, it's just cosine of t. Cosine of t, because the derivative of sine is cosine. So what can I do now? Well, I can calculate second partials if I like. So what is, for instance, f subscript double t? So the second partial of f with respect to t. What is that? Well, I just take the derivative of this thing with respect to t again. And I know that a derivative of cosine is minus sine. So f sub tt is just minus sine t. How about the second partial of f with respect to x? Well, f sub xx, that is the second partial of f with respect to x. Well, I just take my first partial with respect to x and differentiate that with respect to x again. Well, what do I get? Well, 2xy is the same as 2yx, so that's 2yx. And now I'm treating y as a constant, so this thing is a constant, so that's just 2y. I can do exactly the same thing with f sub yy. That's the second partial of f with respect to y. Equivalently, d2f by dy squared. Well, I know that df by dy up here is just x squared. But I'm treating x as a constant, so this thing is just 0. So the second partial of f with respect to y is just 0.